I am so sincerely happy to be talking to you now. I was so sincerely happy to be talking to you when I went to bed last night. And I guess I was so excited I did not wake up on time. But we don't need to get into that. I'm here now. We're going to go over the parts of my presentation that I wasn't able to do in person. Because I really feel bad for my group. They did not rehearse my section, so they couldn't present them. I know they tried, but I really wanted to make sure that they get the grade that they deserve and that we all do well. And also for all of you watching this presentation, I really think there's something valuable here. Professor Bornhorst, Professor Kosiofi, you're already engineers, you already know all this, but maybe you'll find it interesting too. Let's see. So, kind of running over the slides for my associates really quickly, the budget we'll talk about briefly, right after, I think, Mr. Sharma's slide on the testing. So we have two budgets. The actual budget, small budget. This is a graphical representation, don't bother yourself with the table that much. But you will see looking at the table, we only actually bought one thing, two of it, these vents, or these drying racks for $11.50, pretty cheap. Under a $35 budget, team was happy, I was happy. Whenever you look at our actual hypothetical budget, which I actually consider this the more canonical budget, because it factors in the time that we spent, the materials we were given for free by the ESDC and by the TAs, all kinds of things. This is the actual cost, $150.50 of this box, which you would not expect by looking at it, 13 times what we originally thought we were spending. And I think that's really significant. This is effectively what we would be paying if we were paying somebody to manufacture this in a factory. We would be paying for all those services and more. And we're going to get into that later. This is I believe it's Mr. Chu's slide on the summary, and he does a really good job of summarizing it. And what I think he does an amazing job about talking about all these things, the thicker wood. I know he motivates it by saying, when we look at the prototype, this thing is pretty thin. It's supposed to be in a single family household. You can imagine if I was very young, I could break this very easily, not even trying, and if I was young, I would probably try to break it. Whenever we look at some of these other things, prioritize the door, yeah, we have just this mesh screen. We weren't able to build at very high temperatures. Whenever you look at the data, and the data that I think, Mr. Sharma showed, you'll see that it's a lot colder in the device, about 10 degrees Fahrenheit. I think on average, less heat in here. Things dry very badly. Also, and this is kind of the big thing, these process parts begin CAD modeling sooner, perform tests in ideal weather conditions. Why were we not able to do this? And one of the biggest things, why is there no vent? Whenever you look at Mr. Chu's design, there's a vent here. It's a good vent. We all have vents. Basically, we all have vents on this. Why is there no vent? And so, what I want to talk to you about are these things called engineering laws. They're not laws like laws of physics. Newton would be very disappointed. They are heuristics, as in, it's unlike an algorithm which takes in truth and outputs truth. This takes in hunches, ideas, suspicions you have, maybe, or maybe even truth, and outputs other things that might be true, but not necessarily. It's not a truth-preserving process. And so we have two of them, Murphy's Law and Hofstadter's Law. This one you probably know about. I think a lot of people have heard. This one's a bit more esoteric. It's from Hofstadter. He's this weird mathematician guy. He has this book, Gödel, Escher, Bach. Weird book, interesting book, but this law comes from that. Anyways, Murphy's Law, the saying is just anything that can go wrong will go wrong. As engineers, we tend to over-engineer things, and this is basically why, going again into the single-family household application or context of this device, there's a lot of things that are not going to happen in the lab that we should statistically expect to happen in a single-family home. This will get knocked over. If I knock this over right now, it's not going to look pretty. Things like that we have to prepare for, which may not be in our original design specifications because we just can't think of them. And so this is kind of an important thing to keep in mind. And then the way this actually appears in our process, going back to, I'm going to go back slides, I hope you'll forgive me, begin CAD modeling sooner. Why did we begin CAD modeling late? I'll tell you why. Originally, this was designed to be laser cut. The laser cutter at the ESDC broke. We were not able to then laser cut for a month. We weren't able to laser cut this. Because we weren't able to laser cut our parts, we weren't able to, we ended up having to redesign, and then we had to cut our parts late. Mr. Sharma had to go cut the parts in his own home, which was not ideal, and it took a while. Because we had to do that, we also ended up 3D printing late. So we only ended up 3D printing this hinge right here, and no vent. And so it's what I mean here is that a lot of things, or maybe even just one thing, went wrong, and because our plan was not necessarily resilient, we were not able to adapt and bounce back. And then the other thing we want to talk about is Hofstadter's Law, and this is kind of factoring into what I just talked about, but the idea here, everything takes longer than you expect, even when you take into account Hofstadter's Law. This recursive nature is kind of fun. The essence of this is that you cannot accurately predict how long something will take. Typically what this looks like, I think, for a lot of projects is we say, okay, it's going to take us 3 hours to cut all the pieces and put them together in one box. And then you notice, and this happened to us, whenever you're cutting these pieces out, putting the box together, that you didn't actually plan mounting places for these screws. And so now you got to drill, you got to mark out the holes for these screws and drill them and put them in because you got to mount those racks. There's these problems that you cannot expect, you cannot figure out until you're actually doing the thing. And that is one of the ways that Hofstadter's law kind of comes up. But what I think is interesting about these engineering laws, these heuristics, is that they are totally present in all of the engineering we do. We have to expect things that we cannot expect. We have to plan for times that cannot be planned for. And the way we do that is by by making all of these diagrams and charts that show not just what we're going to build and how we think we're going to build it, but also the time we're going to spend. Those project planning diagrams are very important because they let us see, oh yeah, we can actually lose this much time on some factor that we couldn't even predict and still deliver on time. And understanding those is how I think you develop a robust engineering process. And so this is a device, and we learned a lot about engineering, fabrication and design making this device, but even more than that as a team, I think we all learned about how to design a bit more robustly through the experience. Thank you so much for being here. Again, I'm so glad I got to present to you. Have a wonderful night.